All right, so this is part B for homework 4. There we go. It's part B. So for 3 tanks in series inlet flows to the first and second tanks, use Jacobian to linearize the differential equations, obtain state, space A and B matrices. Then use SymPy to determine the transfer functions relating the heights of the 3 tanks to the inlet flows to the first and second tanks. Okay. Compare the response of linear and nonlinear model to step change in flow to the first tank. Alrighty. I went ahead, since none of these parameters were stated in the problem statement, I saw them in the example problem, so I went ahead and just put them down here. So we also have the step change. That's not specified either, but I saw on the example problems that it just had a value of 1. So we'll go ahead and jump into this. So we'll start a very similar way that we did all the way back on homework 1 when we did this. So we'll define an equation for our differential equation, or our change in height with respect to change in time. When we did this in homework 1, we used solve IVP to kind of work backwards, and we integrated all these over a span of t values to give us our graphs. And we'll do a similar thing because we're going to have to compare this to what we did on the last one. But this is how we'll go ahead and start it. So it's going to be a function of time, obviously, and then it's going to be a function of our heights in the 3 tanks, and then also our QNs, or the flow rates into the tanks. All right. So our heights are going to be H1, height 2, and height 3. We have, like we said, inlet flows for the first and second tank. So we have QN1 and QN2. QNs. Right, so now we can do the flow rate out of each tank. So that's a function of the height. The height of the area of the hole. JNP dot square root 2 times gravity times H1. And then it's the same thing for all the rest of these. So then flow rate coming out of 2 is going to be the same thing, but it's a function of the height in the second tank, and then same thing with 3. All right, so now we can pull our differential equations out of this. So dH1 is going to be equal to the flow rate going into the first one minus the flow rate out, all divided by the cross-sectional area of the tank. dH2 is the same thing, but we also have QN2. So we have another flow rate going into Q2, or into tank 2. Also, whatever is flowing out of tank 1 is going into tank 2, so plus Q1 minus what's flowing out, which is Q2, all divided by AC. And then the change in height of tank 3 is Q2 minus Q3 divided by AC. Okay, return, oh gosh, np.array H1, DH2, and DH3. Let me go ahead and run all these. All right, so now we need our initial values. So we need initial values for our flow rate and then also for our height. So we'll start with our flow rates because our heights are going to be a little bit complicated. Our initial flow rates are going to be, and we have those written up here. Is this recording? Yeah, we have those written up here. So that's going to be JNP dot array. So we have our first one and our second one. Okay, now for our initial heights. So we're going to minimize that. We don't want to name the function, so that's just going to be lambda. It's going to be x. This is all going to be solved with respect to x. Lambda x. It's going to be. Gosh, I forgot what comes after this. First of all, I didn't spell minimize correctly. Minimize. So do we need, yeah, we need our x naughts. So that's going to be, so our initial conditions, so it would be DHS is zero, we need an initial guess for, wait, I don't think, yeah, initial guess for our height. So that's, we're just going to guess 10 for all of them. And then an initial guess for Q, which is going to be Q and knots. We have our constraints. So that's going to be this goes. I think it's equals, wait, no. Oh gosh, I always mix up the syntax on this. Okay, I'm gonna have to, we need our constraints and then we need our bounds after this. I might have to stop and double check the syntax on all this. I think our bounds have to be, and then np dot 3. I don't remember the syntax in between though. I'll have to double check that. I'll be right back. All right, realize what we did wrong. First of all, this needs to be 0, and then our initial guess is what's right here. And then our constraint is where we actually define the function. So first we have to say what type of function it is, which is an equation. Then our function equals the variable that we're solving for is h. So it's DHS is TH Q and does it need to be Q and is it the not? I think so. So I think this should be 0 Q and knots. Oh shoot, I forgot my camera. Sorry. What else is over this way? What are we missing? We have too many parentheses. I think so. What do we mess up? 3 were given. Oh boy. Okay. We'll move on just a little bit and then we'll come back to this because I'm sure we're going to mess up on the syntax somewhere else. Now we can start figuring out what our transfer function is. So we're going to need our Jack's Jacobian. So we're going to need the partial derivatives of our function with respect to height, and then we also need the partial derivatives of our functions with respect to qn's, and the Jack's Jacobian basically lets us do that, but it lets us do it for matrices. So we need DHS's, we need position 1, which is our heights variable, and then we need initial conditions, which would be 0 or h naughts, which isn't going to work at the moment, and qn naughts. Is this recording? Yes, it is. We need the same thing, but for Jacobian, there we go. We need the same thing, but for our flow rates. So qn's. So that's going to be position 2. And then same thing. So 0 h naughts and qn naughts. Is that how it's notated up here? Yeah. I know h naught's not defined. Okay. So then our transfer function is going to be, we'll need our identity matrices. So senpai.i, and we need a 3x3 minus our matrices A. This all needs to be and then matrix multiply that by matrix B. Yeah, they're not defined. All right, I'm going to go back and fix what I did wrong up here, and then hopefully everything should run smoothly after that. All right, figured out what was going wrong. My fingers just got ahead of me. All right, there we go. All right, so now we can actually start solving for what our H3 is. Start with our linear one. And like we did in the written portion of this homework, it has to be in deviation variables. So that's going to be our transfer function. So first column at our third row, our step change. Lambda t1. Then, oh, I forgot this. So over to, there we go. The T1. Then for our nonlinear one, we'll do what we did on homework 1 with solve IVP. That's going to be lambda, and then it will be t, and our function, lambda function is going to be the death of me. It's going to be, comma, and then h's, so dh's will need, no, we don't, we don't need our h naughts yet. We'll just do t, h's, and then qn's. So now we need our t-span. So that's going to be, it's going to be 0 up until our last value of t. And we need our h naught. It's going to be h naught. Method is going to be rad do, not dad do. And then dense output, come here, is true. Did I mess up the syntax? Yes, I did somehow. Oh, I messed up right here. All right, we'll come back to that. Let me see if, go ahead and write the code for plotting it. So fig equals make sub, come here, make subplot. There we go. So we'll need the plot for our linear model. So our x's are going to be equal to our t value, and then our y is going to be equal to our, so it's our deviation variables. And like we said, the definition of that is just our variable minus its initial state. So all we have to do is add the initial state to that. So that's going to be h naught. It's going to be the third position. Do we need anything? I always mess up on the figure syntax. Add scatter, and this is our, should be mode equals lines. Our y is equal, it's going to be res.solve values of t, and we want the third one, so it's going to be 2, and then the step function of our first tank. Those lines. Does that need to be, there we go. All right, so obviously this isn't going to work since H3 deviation is not properly defined, so we're going to figure out what I did wrong with the syntax and then come back. Sorry, guys. All right, found where the mistake was. We forgot, this just slipped me. We need our s variable, which is very important for our transfer function. So now that should work properly. Also, one other thing, for whatever reason, I applied that step change or whatever you want to, what do you call it? Step. Yeah, I had a step change in the height, which doesn't make any sense. The step change needs to be on our flow rate. So let's see. Does that put them properly? All right, so there we have it. We have our linear function, and then we have our nonlinear function. As you can see, there's clearly a disparity. That, of course, comes from the, first of all, linearizing the function with our Taylor expansion, and then also any changes that we got from deviation variables. But I think that concludes the second part of. Does this conclude? It concludes part B. Yeah. All right.